In this lesson, we're going to talk about QQPlots a little bit more. So I know there's already a video up where I rambled a little bit about QQPlots. This is going to be a little bit more concrete and actually look at real simulated data and what it looks like. So I'm going to do this in Python. There's a nice tool called Google Colaboratory that allows me to share Python code. So I've put it on that and I've put a link to it just probably above or maybe below, I'm not sure which. But you can go to this and you can actually play with it yourself. I've written a bunch of stuff about how to use it. I'm going to say it in words here, so I'm not actually going to go through. Don't bother reading anything for this. Basically, this is Python code here. If I click this button, it runs that code for me, and so it's imported all the packages and all the functions that I need for this to work. So I'm going to start with the normal distribution, and I'm actually going to put it back to the default of 20. So if I run this code block, again, I get I get simulated data, and that simulated data is shown as a QQplot. And so again, as you saw in the last video, this is always going to be the same value. This is always going to be the same x value. So all of these, none of these x values are going to change. N equals 20 already determines where all of the x values are. This np.random.normal is going to generate random normal variables, and it's going to be different every time I run this code block. So this is genuine normal data. It's got a point down here that's maybe a little bit of an outlier in the negative direction. This is a little bit smaller in the y direction than a normal distribution might expect, and we can see some random little patterns here. This is bound to happen with a normal distribution. If I run this code again, we get a nice little pattern. Again, this is true normal distribution. This is just what QQplots look like for this. I'll run it again. Another little pattern. Let's see if I can get a really bad looking one. This is a little bit bad. The top two values are both quite large compared to the rest. This happens again. This is all perfectly normal in two different ways, I suppose. I could be here forever looking for the right one, or it might be next. I don't know. I'm trying to find one that really doesn't look normal because that happens somewhat frequently. Yeah, maybe I'm not going to find it right now. What you can do with this code, again, you will have a link to it and you can change this yourself. You can make n really small, so n equals 10, and then you can see it's not often that you get something that looks perfectly normal. Points aren't going to be perfectly on the line. Here, I'm just going to leave it at this one. This one kind of looks like, I can annotate, that's right. It kind of has this downward curve shape. So I'm going to leave that there. You can make this really large and see how large sample normal distributions look. I'm going to move on to the chi-square distribution. You don't need to understand the chi-square distribution at this time. Just know that it's a right-skewed distribution. So when I sample data from this distribution, most of it's going to be in the center. There are going to be some large outliers, but no small outliers. So this is what right-skewed means. We've got a small tail on the left, big tail on the right. If you had put, the way I like to explain it is if you put peanut butter right here in the middle, and then you push it to the right over your bread, you get a right skewed distribution. So this is the same sort of thing. Again, I've got n equals 20. I've got generating chi-square distributions this time. And this is one realization of it. We get this sort of, it looks like an upward curve shape. And I'm just going to leave that on the screen as I generate more. So I generate another one, not as perfectly like this, not as perfectly along this curve. This actually, if I saw this data, it looks normal enough to me. The normal distribution can be quite different. I can change a lot. This also looks normal enough. Sometimes it looks closer to this line. Sometimes it doesn't. With 20 observations, it's very difficult to tell. So if I up this to 200 observations, then it's very obvious that all of these points are above the line, all of these points are below, and then we're back to above. We don't, again, from the previous video, it's points down here that are big outliers in the negative direction and big outliers in the positive direction. We have no outliers in the negative direction, but we do have in the positive direction. And so we get this shape. And if I do n equals 10 and run this code a couple of times, you're not going to be able to tell this from a normal distribution. You don't have enough data to really tell. Even this, it looks very much like that curve that shows a right skewed distribution, but it's really hard to tell. Left skewed data, I just took the chi-square distribution and flipped it so that it was backwards, so that it's left skewed. If you take it and flip it, it's yeah. And we get this sort of curve. There's big outliers in the negative direction. In the positive direction, there's nothing up here. All of it goes down, and then there's big outliers in the negative direction. And not necessarily outliers, there's just more data in the negative direction. It's more spread out in the negative direction and more compact in the positive direction. I shouldn't say this in terms of outliers. And then we've got a t-distribution. So this black distribution is the t-distribution and red is normal. So you can see that the black, let's use black ink, black is spread out a little bit in the tails and then down a little bit in the peak, whereas red is brought in at the tails and up. So this is a wide tail distribution. It's got more weight in both directions when compared to the normal distribution. It's got more weight down here and more weight up here with less weight in the middle. So when we do that, this is with n equals 500. T-distribution and normal distribution are quite similar, but with t equals 500, I'm going to switch back to my nice purple color, we have outliers, or we have more weight than expected in the negative direction and in the positive direction. So that's where we get this shape from. And if I keep running this, I mean, it's 500. It's going to look basically the same every time, just a little bit shifted, I guess. My original drawing, this actually, if I saw this data in real life, I wouldn't have any problem with calling that normally distributed. It's close enough. Whereas, yeah, this one is where I might start saying there's a little bit of a problem in the lower tail. Upper tail's maybe not perfect, but there's maybe a problem. And just like before, if we have n equals 10, I'm going to get rid of this. We don't really have enough chance to say whether or not this is normally distributed. We don't have enough information here. In this one, it almost looks like that. I'm going to let you guess. It's not very high down here, but we have lots of points up here. So take a second and think, which one was that? Is that right skewed, left skewed? What's going on with that? I'll actually just leave it there and have that. I'll let you think about that, maybe go back in the video. I've rambled long enough. So that's sort of, I guess the main takeaway message from this is a lot of normal data doesn't really look normal, but a lot of data that is not normal does end up looking somewhat normal, and this is one of the reasons that you can generally use the normal distribution. There's lots of variance in that. It's linear modeling especially is pretty robust to violations of the normal distribution.